be bringing in atmospheric results at that point. I do want to report one piece of news, but it's more or less operational, and that is that the ALICE ultraviolet spectrometer got a great data set to the ground from the UV solar occultation, in which we're already learning things about Pluto's atmosphere, so stay tuned for Friday on that. So with that, I'm going to turn it over to Hal Weaver, who's our project scientist. Hal's going to give you a little bit of hydrotherapy. Hal?
Thank you very much, Alan. Well, Pluto and Sharon are going to steal the day today. I mean, this can be these awesome images that you'll see in a few minutes. But let's not forget that Pluto has 4 small moons as well that we want to collect data on. Starting from closest to Pluto and going out is Styx, Nix, Kerberos, and Hydra. And this morning we got the first really well-resolved images of Hydra, which is shown in front of you here at the native scale, 2 miles per pixel. This is about the same number of pixels across Hydra that we had across Pluto in mid-June. And so we're ecstatic about this. Prior to the New Horizons revealing of Hydra here, we were completely uncertain about how big Hydra was. It could have been anywhere from 20 miles across to almost 100 miles across. New Horizons has made it easy. Just count the number of pixels across. 28 by 19 miles, an elongated object. Hydra is not a planet. It's about 30% larger in one dimension than in the other. But there's some very interesting things about Hydra. You see some variations in the brightness across the surface. If you can go to the next slide. This shows, what we did here was actually subsample the image by a factor of 4 from the native, so it's 4 times subsampled to take away that pixelated look, and as well as overlay contours showing the brightness changes. And we took cuts across to measure that's the approximate places where you have the longest dimension in the green and the shorter dimension in the yellow. The surface of Hydra is surprisingly large. It's about 45% reflectivity. So about 45% of the sunlight incident on it gets reflected away, and that can only mean that Hydra surface is probably composed primarily of water ice. It's the only way to get it that bright. And that's cool. It's intermediate in brightness between Charon and Pluto. A nice thing about what we have coming up, actually, some more observations of Hydra, which will be even higher resolution, about a factor of 2 or 3 better. And so we're looking forward to those, but it's great. We've already seen Hydra revealed, and it looks very interesting. Thank you.
Okay, very nice. Will Grundy leads our composition team and is going to report some results that they've obtained.
Okay, so the Ralph instrument is the instrument that we're relying on mostly for surface compositions, and it's composed of 2 parts, the color camera, MVIC, and infrared imaging spectrometer called LISA. We don't get any data down today from either of those instruments, and so what I'm showing you is some data that came down in the failsafe data set that came down overnight between the 12th and the 13th. So this is a little earlier. This is a base map that's just showing you the geometry. You can see that the heart region is just rotating on, so this was a little while ago. Could I have the next time step? This is an overlay of LISA data. So what I did is each of those large blocky pixels, about 150 kilometers across, is an infrared spectrum. And the value of an infrared spectrum is that it tells you what that pixel is made out of. We're going to get much higher resolution data than this, but this is what's in the can now in the failsafe data set. These colors are just 3 infrared wavelengths. We get 256 infrared wavelengths, so we could make an enormous variety of color maps to pull out specific compositional information. This particular one is focusing on methane. I put a absorption band that's at about 1.65 microns into the blue color channel, a continuum region between 2 methane bands into the green channel, and a a much stronger methane band into the red channel. And all I'm doing here is showing, again, at lower resolution than the color images yesterday, the diversity of terrains. What I'm going to do now is pick out a couple of specific regions, although you can see that there's many different regions here. So if I could get the next time step, please. These two regions of interest, one's a 3x3 pixel block, another one is a little squiggly thing that's in one of the dark regions. So I'm concentrating on the polar cap, and I'm concentrating on one of the dark regions. And if we go to the last time step that I have, these are the two spectra that you pull out. And you can see that they're quite different from each other. They both have methane, but the overall shape of the spectrum is very different, and we can really be spending years modeling these and thinking about what they tell us. There's a lot of information. We only have a small subset of the wavelengths at this point because we just don't have the bandwidth to get more down. But this is providing a lot of information about the different regions and how they work.
Thank you, Will. Yesterday, we showed you a beautiful image of Pluto that was made just before the closest approach and sent to the ground as a part of those fail-safe data sets. Today, we're going to show an image of a similar resolution on the big satellite Sharon, and Deputy Project Scientist Kathy Olkin is going to discuss those results.
So originally, I thought Sharon might be an ancient terrain covered in craters. Many people on the team thought that might have been the case. And so Sharon just blew our socks off when we had the new image today. So if we can pull it up so you can take a look at it. I don't, yeah. So we were just been thrilled all morning. The team has just been abuzz. Look at this, look at that. Oh my God, that's amazing. So I'll walk you guys through some of the things we've seen in the image and tell you what we're thinking about. And I'm going to start in the north and kind of work my way down. So you've seen the darkish area that is at the North Pole. And informally, we've been referring to that as Mordor. So that's awesome. So Mordor is the darkest area near the pole. And you can see this is a natural color image. And so the red around it, the red coloring that we've seen, extends beyond just the deepest, darkest part of that polar region, Mordor. And we think that the dark coloring could perhaps be a thin veneer. You can see locations at the North Pole where a crater has perhaps dug into that region and excavated underneath it. So you can see those brighter regions that may be craters. And so that's part of the reason why I say that we think it could be a thin veneer. So let's see. And also you can see that that area is kind of a polygon shape. So there's, and then the red color is more diffuse around it. Moving down across a little bit lower, going from the northeast to the southwest, is a series of troughs and cliffs. And that's just striking to me. It's amazing to see this image. They extend about 600 miles across the planet. So this is a huge area, and it could be that it's due to internal processing, and we will be looking at that in more detail. Just below that region, the line that you see cutting across from the northeast to the southwest, more east-west than north-south, is a region where it's relatively smooth. There's less craters. So perhaps it's been geologically active or recently resurfacing that area. So that's very exciting to see as well. Two features that I want to go back up a little bit higher on the near the top at about the 2 o'clock position, you see a canyon. You can see a long linear feature, and you can actually at the very top see kind of a notch where you're looking through to the space on the other side. And that canyon is really quite deep. It's about 4 to 6 miles deep. I find that fascinating. So it's a small world with deep canyons, troughs, cliffs, dark regions that are still slightly mysterious to us. There's another canyon on the other side at maybe the 10 or 11 o'clock position, and that one is about 3 miles deep. There is so much interesting science in this one image alone. And we have a higher resolution image that we'll get that won't cover the whole Olive Sharon, but it'll cut across the northern part, and we'll get some of the dark area and then some of the middle area. And it's going to be about a factor of 5 better in resolution. So as we've been saying, Pluto did not disappoint. I can add that Karen did not disappoint either. Thank you.
Well, yesterday when we showed that beautiful image of Pluto, we noted that we would have imagery with 10 times the resolution on the ground by today. And in fact, John Spencer is going to tell us about just the first frame of that mosaic that's already down on the ground, and which has already given us a big surprise. John?
Thank you, Alan. So yeah, we've got a whole bunch of high-resolution observations now safely on board the spacecraft, and this is just a taste, just one small part of one of those observations. And if I can have the first slide, don't get excited yet. This is what you see. This is what we saw yesterday, and this is a spectacular image. But we now are focusing in on small details on this amazing world. Before I go to that, I should say that we now have an informal name for the heart. The heart is a good name, but we want to honor the discoverer of Pluto, and this is now, we are calling this Tombaugh Regio. And so if I can have the slide back, we are now going to focus on a small region just near the bottom of this image, which is near the day-night line, where we have shading that throws the relief into sharp focus. And so we're going to be focusing on an area just a little bit to the left of the bottom of the frame. And if we can now run the movie. Okay, so we're zooming in on this area. Here's the image, here it comes. Yeah, that was our reaction too. So this is a small part of a mosaic that covers the whole of Tombaugh Regio and regions around it, covering quite a variety of terrains. But this is one of the first things that really caught our attention. This area, as you can see from the scale bar, is about 150 miles across. We're seeing features as small as half a mile here. You could see the APL campus on this kind of image. The most stunning thing about this, well, there's many stunning things, but the most striking geologically is we have not yet found a single impact crater on this image. This means this is a very young surface because Pluto is being bombarded by other objects in the Kuiper Belt, and it's bound craters happen. So we just eyeballing it, we think it has to be probably less than 100 million years old, which is a small fraction of the 4.5 billion year age of the solar system. It might be active right now. With no craters, you just can't put a lower limit on how active it might be. These mountains here that we're seeing were quite spectacular. These are up to 11,000 feet high. There may be higher ones elsewhere. Now, we know the surface of Pluto is covered in a lot of nitrogen ice, methane ice, carbon monoxide ice. You can't make mountains out of that stuff. It's just too soft. It doesn't have the strength to make mountains. So we are seeing here the bedrock, or the bed ice of Pluto. We're seeing the icy crust. Water ice is strong enough at Pluto temperatures to hold up big mountains, and that's what we think we are seeing here. So the nitrogen and the methane are just a coating on top of this icy bedrock, and we're seeing that here. Now, what's particularly exciting to me about this is the first time we've seen an icy world that isn't orbiting a giant planet. All the other icy worlds we've visited have been moons of giant planets. And we see strange geological features on many of these moons, and we often or usually attribute this to tidal heating, deformation of these worlds by the gravity of that giant planet and interactions with other moons. That can't happen on Pluto. There is no giant body that can be deforming Pluto on an ongoing, regular basis to heat the interior. Charon is just too small to do that. So this is telling us that you do not need tidal heating to power ongoing recent geological activity on icy worlds. That's a really important discovery that we just made this morning. So I know this is just the first of the many amazing lessons we're going to get from Pluto, and there'll be more on Friday. We'll have more of this mosaic to show you on Friday, which is going to show equally amazing things, I'm sure. So stay tuned.
Right, and I'm going to follow up on this same image so we can leave it on the screen for you to enjoy. I'll tell you another couple of implications that we've reached as a result of this discovery. Just to expand on what John last said, which is very, very important, we now have an isolated small planet that's showing activity after 4.5 billion years. We thought this might be the case after Voyager 2 discovered that Triton, orbiting Neptune, also has virtually no impact craters. But we couldn't be sure for just the reason that John said, because there's always an out that tidal energy could have powered activity in tidal energy due to breaking into orbit around Neptune, could have been powering the activity on Triton. So that may have been the case for Triton, but it can't be the case for Pluto, and now we've settled the fact that these very small planets can be very active after a long time, and I think it's going to send a lot of geophysicists back to the drawing boards to try to understand how exactly you do that. There's another implication, and sometimes things work out in science. A couple of months ago in May, Kelsey Singer, who's a postdoc on this project, and myself submitted a paper to the